Thank you for attending my presentation. I am Yoon-Sung Cho with Wireless Networking and Communications Group at the University of Texas at Austin to present coordinated multi-cell beamforming and power allocation for Massive MIMO with low-resolution ADC and DAC. Generally speaking, Massive MIMO or large-scale antenna systems are one of the key technologies that enable modern and future communication systems because of its significant gain in spectral efficiency and capacity. However, since each antenna is usually equipped with an RF chain with two 16-bit data converters, overall power consumption eventually goes up dramatically. As a low-power solution, we can choose to deploy low-resolution ADCs and DACs with typically 2 to 4 bits, since power increases exponentially with the number of quantization bits, P. Okay, here's the problem statement of this work. The problem we define is to minimize total transmit power under coarsely quantized systems, such that a target SINR is satisfied. However, we have several impairments to consider. First, non-trivial quantization error from low-resolution data converters needs to be considered carefully. Also, because of the multi-cell scenario, the solution has to be designed by considering thermal noise, intracell channel, and intercell interference. Therefore, the main purpose of this work is to design the optimal power allocation for uplink direction and the optimal beamforming for downlink direction by forming total power minimization problems with targeted SIN. We introduce strong duality between uplink and downlink problems, as well as centralized and distributed algorithms to jointly solve them. Okay, here's the system model. We have NC hexagonal cells with a dedicated base station in the center. Each base station has NB antennas with low-resolution data converters. And each base station serves NU users with a single antenna and infinite resolution data converters. We assume sub-6 channel models with time division duplex. Here, H sub JIU means the uplink transmission path from user U in cell I to cell J. Also, H Hermitian is the downlink transmission path because of the TDD assumption. For analytic tractability, we utilize additive quantization noise model, AQNM, based on previous researches. We can linearize the nonlinear behavior of coarse quantizer using quantization gain alpha and uncorrelated quantization noise. In the uplink model, we have dedicated user in ith cell, interference from other cells, thermal noise, and quantization noise. In the downlink model, each user receives the desired path, intercell interference, as well as inter-user interference, quantization noise, and thermal noise. Here, we have two main problems. One is the quantization gain alpha, which is typically smaller than 1, and strong interference here and here. We first formulate the total transmit power minimization problems for both uplink and downlink cases when the base stations are equipped with low-resolution data converters. As you can see here, the SINR expressions are coupled with quantization error here and here. However, at this point, they are two separate problems. And then we prove duality between two problems. We first simplify the max operator in the uplink constraints by using MMS equalizer that maximize the SINR. We then take a Lagrangian dual of the downlink problem and show that it is eventually equivalent to the uplink problem with MMSE equalizers. On top of that, we prove that there's no duality gap. The workflow is to prove that the downlink problem in P2 is actually an instance of second order cone problem, a convex problem, and to prove that the downlink problem is strictly feasible at the end. Okay. Inspired by strong duality, we obtain the optimal omlink solution, as you can see in the box. These are obtained by setting the derivative of Lagrangian to 0. Here, you can follow this proof. However, you can see that the solution includes H and K. H is the dedicated channel which is known, and K is the covariance matrix of received signals, which potentially includes intercell interference, as you can see here. And capital lambda is a diagonal matrix with transmit power from all users as its diagonal terms. It turns out the covariance matrix can be estimated locally without the explicit knowledge on intercell interference by collecting several pilot signals. This means we can apply a distributed manner. Lastly, we also derive the optimal downlink solution based on the strong duality. So here's the proof. Assuming that the optimal beamformer W is a linearly scaled instance of MMSE equalizer F here, so we can think that W equals square root of tau times F. So we plug this formula into the downlink constraints. The constraints are satisfied when using tau from solving the system of linear equations, as you can see here. All right, we have written down the algorithm that can jointly solve both problems. Essentially, it summarizes the result we've introduced so far. For an arbitrary initial point, we compute the lambda values iteratively. Since K involves all lambdas in computing a single lambda, we designed an iterative algorithm that finds a unique fixed point. Here, the update of lambda affects K matrix only. And then, using the converged optimal omlink solution, we further compute the associated omlink MMSE equalizer, which gives the optimal downlink solution based on the corollary 3. We also proved that this algorithm converges to a unique solution regardless of the initial points, unless it is zero initialization. Okay, then let's move on to the simulation results. We plot target SINR versus total transmit power, and B means the number of quantization bits. We compare our algorithm against the Purcell approach. Red lines are our algorithms, and blue lines are Purcell approaches. With 16 antennas, the Purcell approach easily diverges in low SINR target. However, our method diverges in medium SINR, here and here. With 128 antennas, which is considered as Massive MIMO, our method shows divergence with only 2 bits. However, the Purcell approaches show divergence in the medium SINR target. Here, this figure validates the strong duality between omlink and downlink problems. We first plot the omlink cases with red lines, and we place the downlink results with blue markers. Since they are matching together, we can observe the strong duality from this figure. And this is the CDF of the achieved SINRs. So our algorithm is in red line, which gives us clear spike at the target SINR. So In this framework, our target SINR is 0 dB, and you can see a clear spike at the target SINR. So our algorithm properly coordinates with other cells, consuming no more and no less than what the system requires. Here, pink line and green line are the locally estimated using the locally estimated covariance matrix K. We average out NP pilot signals to get the estimated covariance matrix. Even though we cannot achieve the target with 100% probability, but the deviation from target is not very big. Here, deviation is here and here. It turns out using more pilot signals achieve the target with higher probability, with lower deviation from the target. And blue dotted line is for the Purcell approach. And it turns out the CDF has a larger deviation from the target with implausible power. So this is totally impossible, implausible power. In conclusion, we designed power allocation and beamforming through total transmit power minimization problems with low resolution data converters and targeted SINR. For a better analysis, we proved duality, strong duality, optimality, and guaranteed convergence. We finally proposed an iterative algorithm that can jointly solve both uplink and downlink problems based on the strong duality we showed. We also suggest the distributed algorithm with locally estimated covariance metrics at each base station. Here, one promising extension of this work is to add Purcell antenna constraints for a more realistic scenario. Thank you for your attention.